Imagine a giant whip cracking. That sharp, loud sound, that's a sonic boom, but on a smaller scale. Now picture a jet airplane flying faster than the speed of sound. It creates a similar crack as it breaks this speed limit. This crack is called a sonic boom. It's a powerful sound wave created by an object traveling incredibly fast. Sonic booms are not just loud noises, they are physical events with real-world implications. Understanding sonic booms helps us comprehend the physics of sound and its limitations. It also has practical applications in aviation and aerospace engineering. To understand sonic booms, we need to understand sound itself. Sound travels as waves like ripples spreading on a pond when you throw a pebble. These waves travel through air at a specific speed, about 767 miles per hour. Think of a boat moving on water. As the boat moves, it creates waves that spread out from its bow. Sound, like these waves, also has a speed limit in the air. This speed is called the speed of sound. The speed of sound is not constant. It changes with altitude, temperature, and humidity. However, for simplicity, we'll consider it a fixed value for now. Now imagine our boat going faster and faster. What happens to the waves? They start bunching up in front of the boat. The same thing occurs with sound waves when an object, like an airplane, approaches the speed of sound. When the airplane's speed matches the speed of sound, it's caught up with its own sound waves. These waves pile up, creating a region of high pressure in front of the aircraft. This is called the sound barrier. Breaking the sound barrier requires immense power and a special aerodynamic design. Once an object crosses this barrier, it's traveling at supersonic speeds. As the airplane continues flying faster than the speed of sound, it pushes these compressed sound waves out in front of it. This creates a cone-shaped shock wave that trails behind the plane. Think of this shock wave as a moving wall of compressed air. It's similar to the wake a boat creates, but instead of water, it's a disturbance in the air itself. This disturbance carries a significant amount of energy. The shock wave doesn't just move backward, it spreads out from the aircraft in all directions, carrying the energy of the sonic boom. The thunderous roar, why we hear the boom. When this shock wave, this wall of compressed air reaches our ears, we perceive it as a loud boom. It's like the air itself is suddenly cracking under pressure. The intensity of the boom depends on several factors. Distance from the aircraft, its size and shape, and even atmospheric conditions can influence the loudness of a sonic boom. For people on the ground, it can sound like a clap of thunder or a loud explosion. This powerful sound wave is not just an auditory experience, it can also cause physical vibrations. While not typically destructive, it highlights the energy involved in breaking the sound barrier. Sonic booms are most commonly associated with supersonic aircraft, particularly military jets like the F-16 or the Concorde. However, any object traveling faster than the speed of sound can create a sonic boom. Even a simple bullwhip can create a miniature sonic boom. When cracked, the tip of the whip can reach supersonic speeds, producing a sharp cracking sound, which is a small-scale sonic boom. Meteors entering the Earth's atmosphere also create sonic booms. As they travel at incredibly high speeds, they compress and heat the air, generating shock waves and the characteristic sonic boom. Sonic booms can be disruptive and even harmful, especially in populated areas. That's why there are regulations and ongoing research on how to mitigate their effects. Aircraft designers are exploring new aircraft shapes and technologies to minimize the strength of the shock waves they generate. One approach is to create a more elongated, stretched sonic boom that dissipates energy over a larger area. Other research focuses on manipulating the airflow around the aircraft using advanced engine technologies. The goal is to control and soften the impact of the sonic boom on the ground. You might wonder, if spacecraft travel much faster than sound, why don't we hear sonic booms from them? The answer lies in the environment of space. Space is a near-perfect vacuum, meaning it's almost entirely devoid of matter. Sound waves, which need a medium like air to travel, cannot propagate in the vacuum of space. Therefore, even though spacecraft travel at incredible speeds, they do so in silence. There is no air for them to compress and create the shock waves that we perceive as sonic booms. Research into sonic booms is not just about reducing their negative impacts, it's also about exploring their potential applications. For example, Scientists are studying how to harness the energy of shock waves. In the future, we might see new aircraft designs that minimize sonic booms, allowing for faster travel over land. Understanding and manipulating sonic booms could be key to unlocking new possibilities in aviation and beyond. As we continue to push the boundaries of speed and technology, understanding the physics of sonic booms will remain crucial for ensuring safe and efficient travel in the years to come.